Evening, everybody. 5 o'clock on Thursday means it's time for some Calc 3. Today's going to be a kind of a cool day. We're going to do some triple integrals. You guys saw in the online lessons. So before we get to that, just a couple quick reminders. Number one, we're about halfway through this module. I guess a little further than halfway. These modules are a little longer than what we had in the first half of the semester. There were 3 modules in the first half, and now we've only got 2, but there's more sections. So we still got a little while before the next quiz. Make sure you pay attention to that. We'll be finishing up this module next week, I believe. Maybe the week after. So I wanted to remind you of that. Also, the first take-home problem will show up after class tonight. Not that we've covered necessarily everything that's on it, but we've done, we haven't done the entire module, but I wanted to keep the same pace on the take-home problems as if we didn't have that extra week of spring break for anybody who still wants to complete the class on the regular schedule. So I kept all the take-home problem dates the same. So that'll be showing up after tonight. And that's something you guys can go ahead and get started on. Those are not due until the scheduled final in Moore, which I want to say is like May 20th. So, well over a month away. But you guys know now you guys have some experience with the take-home problems. They can take a little bit of time. So this will give you the opportunity to get started on them early and work on those. Like I always say with the take-home problems, I encourage you to use technology as much as possible to solve your problems. You do not have to solve them by hand. You can, absolutely, but there's going to be some tough iterated integrals in the take-home problems, as you can imagine. So feel free to use Wolfram Alpha, Symbolab, Maple, any program that you want, that you find helpful. As we discussed before, just make sure you put in an image, you include a picture of a screenshot of what you entered and what you got from the program. That'll 100% count for your work. All right. Okay. So I want to get into today. We're only doing the one section, but because there's some interesting things going on with triple integrals. Now, on the one hand, all we're really doing is adding another integral to our double integral. So from a computational standpoint, there's nothing really new other than now we have to integrate 3 times instead of 2. So it's like just adding another integral symbol outside of what you were doing before. The bookkeeping gets a little bit messier because you have to do 3 integrals, but procedurally, it's something you guys have done and something you guys have gotten good at. Where triple integrals get a little more difficult than double integrals is our region of integration is now a 3D region instead of a 2D region in the XY plane. So it becomes much harder to visualize. It's harder to draw. It's significantly harder to draw by hand. And so that's what we're going to focus on in our full class discussion today. I am going to go through a few different problems and really try and discuss how I'm getting my limits of integration. That's really what I want you guys focused on for class today, is how we're finding the limits of integration. And then depending on how much time we have after the ones that we go through as a full class, hopefully we have a time to break you up into groups and let you at least try 1 or 2. We'll see how that plays out depending on how many questions and how long it takes. But I really want to focus on how we get the limits of integration. All right. So without any further ado, let's jump into triple integrals. Obviously, if you have questions about take-home problems, things like that, you can always ask me at the end or after class. I don't want to pretend like say that I'm not going to take any of those questions. Just right now, I want to get into the material so we have more time to spend on it. Okay. All right. So now we can integrate a continuous function of 2 or 3 variables over a solid region W, just as we can integrate a function of two variables over a flat region in 2 space. We can also create a Riemann sum for this. Now that's not what we're going to do, but basically what happens is we break up that 3D model, the 3D region, into a bunch of 3D cubes. Those would be the rectangles from our Riemann sums way back in Calc 1. In this case, we do it into 3D cubes, and we basically let go until we have infinitely many cubes to give that whole region. So here's what it looks like as a Riemann sum, right? We have 3 summations, one for each variable. And I don't want you to worry about this. We're not going to be doing Riemann sums in 3D. The only reason that I show this is to continuously make the connection between what we're doing now and Calc 1. In Calc 1, we would have just done this inside one with a function of one variable. The y and the z would have been gone. That is our Riemann sum from Calc 1. If we get rid of the z and then we go to the next set of parentheses, that's our Riemann sum for double integrals. So all we're doing is really adding this third dimension on top of it. So again, procedurally, all we're doing is adding another layer of integration. Now, just like with double integrals, when our region is a box, in other words, when all our limits are constants, that's our easiest case because we know what our limits are and the order truly does not matter. We can do it in any order that we think is going to be easiest. All right. So this triple integral, if these were all constants, those create some rectangular solid, and we can change the order. And there are 6 orders of integration because we can, go through all the possibilities of doing each one first, doing each one second, doing each one third. Now, what I want to focus on, like I said, today is how do we get those limits? All right. So we're going to look at a few examples. I'm going to do some that are from the worksheet. And we're going to take a look. We're going to look at the 3D plot and see how we take the 3D plot to create the limits of our limits of integration. But let's start off with the easy case. So if W is a rectangular box, we know, again, it's not even a question that if it's a rectangular box, all of our limits are constants, in which case the order doesn't matter. And so, like I said, we would do whatever order we think is going to be easiest. And in a problem like this, they're all pretty easy. So if we wanted to do this triple integral, and we're integrating over a function, e to the x plus y plus z, we can do any order we want. We can see that, x is going to go from 0 to a. So maybe we do x first. That would put the dx here. Y is going to go from 0 to b. That would give the dy. And z is going to go from 0 to c, and that would give our dz. So again, this one's pretty easy to set up, and it's actually not a bad integral. It's not nearly as bad as it looks. This could be rewritten as e to the x times e to the y times e to the z, and it's just a matter of going through 3 times. I'm not going to actually do any by hand on the triple integrals today. You guys saw a couple in the video lessons, and again, depending on how much time, hopefully you get a chance to maybe try one today, but you're obviously going to get a chance to try it in the homework. You've done double integrals. All we're doing is adding another layer of integration. So I really want to focus on how we get the limits. Another thing that I want to point out, and I didn't talk about this with double integrals, but I want to point it out with triple integrals. One of the questions I get quite often, especially in Calc 1, is about the dx and why do we need it? And, in theory, we could do an integral without the dx. It represents that infinitely small rectangle width, or in this case, that infinitely small length of one side of our cube. But hopefully you've noticed with the double integrals and now with the triple integrals, they actually serve a much more important purpose, because now they tell us what our order of integration is. So this is telling me I'm integrating with respect to X first, then Y, then Z. So they become a lot more important for us than they maybe were in Calc 1. And again, it's a question I get a lot. Why do we always put it in there? I can do it without it. Now it becomes much more significant, because now we're specifically denoting, or the problem specifically denoting, the order of integration. Okay. All right. So that's our first example. Like I said, that's not one of the more interesting ones. Let's go to something a little more interesting. And guys, if you have questions as I'm going through these, feel free to stop me and ask. Like I said, my goal is for you guys to feel better or feel more comfortable about finding the limits of integration. So I want to spend as much time on that as we need. Okay, let's talk about sketching the region of integration. The reason I want to do this is I want you to get used to forming the connection between what's here in the integral and what the plot looks like. So let's, for notes purposes, let's say that was example 1, and this will be example 2. And so we've got this integral from 0 to 1 in the X direction. And I know that again, because of the dx's on the outside. And then we got the Y's, the Z's. Then we got the Y's. And we're integrating over some function. And dy, dz, dx is our order of integration. Now, again, this tells me that these limits are y values. So let's talk about plotting this. This is not going to be a pretty picture because I am doing it by hand. And I'm not going to ask you to be sketching a whole bunch of regions of integration by hand, because it's not trivial. But I want to help, like I said, make that connection between what's going on here and what's going on here, and how you get those limits from a graph. All right, so now the conventional way of doing this is the positive x-axis, this is the positive y-axis, this is the positive z-axis. We don't always draw on the negatives. We'll put them on as dotted lines if we need them. Now, this is going to be something you're going to be seeing a lot. We've already seen it a couple times. And if you're not familiar with it yet, you will be. What this is, because it's for y, that's the curve, y equals square root of 1 minus z squared. Now, that's a half circle in the YZ plane. If you're not sure why, we did this, I think last class or maybe the class before. Square both sides, add the z over, and you get the formula for a circle of radius 1. By taking the square root, we can only get positive y values. So it's in the YZ plane because those are our two variables. We know it's going to be circular because of the format, and the radius is going to be 1 because this number here is the radius squared. So that's how I know all that stuff. So I am going to throw in the negative z-axis because I have to go down there, because I see that in the y, I'm going from 0 to square root of 1 minus z squared. So I'm not going over here into the negative y's. So let's say 1's about right here. In the YZ plane, I've got something that's circular. All right, so let's use your imagination and pretend that that's a circle, half circle of radius 1. Okay. That is what those first two limits are telling us. Now, if this lower limit had been negative square root of 1 minus z squared, then we would have included the negative side, because that would have given us the other side. Like I said, you guys are going to get really used to seeing the circular stuff. That's going to be a lot of our regions. So if you're not comfortable with it yet, don't worry. It's still fairly new. But I promise you, after you do this section, you will get so used to seeing circles and spheres, you'll recognize it right away. Okay. Now, in the Z direction, we're told we're going from -1 to 1. Well, that's encompassed with our top half of the circle. -1 to 1 in the Z direction, because those are Z values, because this guy is DZ. So the last thing is X, and X only goes from 0 to 1. Notice there are no equations on these limits. So I'm not getting any curve in this direction. That's telling me, you know, it's going to come straight out, and we're going to come out to where X is 1. Oops, let me change that back. We're going to go out to where X is 1. And basically what's going to happen is it's going to extend this figure out to where X is 1. And I'm going to do my best to draw this. And what we get is basically like half a cylinder. All right, that would be our solid. I apologize for the awfulness of my drawing, but hopefully you can kind of see that structure. We get the half circle in the YZ plane, and that's because of these first two sets of limits. That's what's telling us the half circle. And then we get this thickness or the height of the cylinder because X goes from 0 to 1. So that would be the region of integration for these given limits. Any questions about that one? And that was our only goal on this one, was to draw the region of integration. We weren't trying to integrate it or anything crazy like that. All right, so far so good. Let's go on to another example. Now let's go the other direction. Let's take a region and make it and turn it into limits. All right, so we're asked to find limits for this integral. It's another example. So we're going to have a triple integral. And like I said, this is going to be what you guys are focused more on today when we split up into groups. I'm going to have you solve your integrals with technology. I want you focused on the limits. All right, so it's kind of hard to see because you can't really rotate this guy. So let me do this. Here's the region. It's a quarter sphere of radius 4. Okay, so we're in the first, that upper positive part of the plane, but notice in the X, it goes positive to negative. All right, so let's talk about how we do this. So first thing we need then is we got to remember the formula for a sphere of radius 4. It's X squared plus Y squared, plus Z squared equals 4 squared. Very similar to the circle we had on the third one. Now, depending on what variable we do first, we're going to solve it for that variable. And maybe we'll do this one in a couple different orders. That's the thing, guys. There's an infinite amount of, no, I shouldn't say an infinite. There's not an infinite, but there's a lot of ways to set up these integrals that will all work. So you guys are going to have a little bit of what you prefer, what you think is going to be easiest. And there are going to be some times where one is easier than the other, for sure. And we'll talk about that too. But on something like this, you know, it's not going to make a huge difference. So let's say we decide to do Z first. Okay. Look at what happens with Z. I go from the XY plane up to the sphere. So that means I need to solve the sphere for Z. So Z equals square root of 16 minus X squared minus Y squared. Like I said, you're going to get used to seeing this form a lot in this section. So we're going to do Z first. And Z is going to go from 0 up to the sphere, which is square root of 16 minus X squared minus y squared. All right, we're done with the first limits of integration. And honestly, if you can do the first limits of integration, it gets easier because the rest is like setting up the limits for a double integral, which you guys already have practiced with. So what you do next is you look at your region or your shadow region in the XY plane. In other words, what does the shadow of this thing look like in the XY plane? Well, we can kind of see it from here. If we put X on our horizontal and Y on our vertical, we can see that it comes out here to Y, out to 4, and that at X, it goes from -4 to 4. And so this is our region in the XY plane. Again, this is now a problem of doing a double integral. So we would do the area between curves. I think it's plenty easy to do Y next, because we know that this is square root of 16 minus X squared. And there's two different ways to get that. Number one, we know we have a half circle of radius 4. Well, that's a half circle of radius 4. All right. What if we weren't sure about that? Or what if we had something a little more complex? Well, we're now in the XY plane, which means we get to hold Z constant. So that means because we're in the XY plane, we can set Z to 0. And that gives us X squared plus Y squared equals 16, which solving for Y gives us radical 16 minus X squared. All right. So I can't stress that enough. Once you get a top and a bottom, or a left and a right, or once you get that first set of limits in your triple integral, it really does become a double integral problem as far as finding the other two sets of limits. So we know from our practice that goes from 0 up to the curve. Square root of 16 minus X squared. All right. And we know that X is going to go from here, which is -4, out to 4. And there's our last two sets of limits. And just because we now know our order, dy, dx. This is not the only order to do this one in. All right, let's do a different order. All right. But first off, before I do a different order, any questions about that one? All right. So alternates. All right, so we're still going to integrate over f of x, y. Sorry about that noise, guys. Z, because that's our function. Let's do x first. This is one we can really do in any order. Again, it goes back to what you think is easiest. A lot of times I do Z first if it's possible, but sometimes it makes sense to do another order first. But I want to do x first for a very specific reason. X is the only one that goes both positive and negative. Now, x goes out to this side of the sphere and then to this side of the sphere. We can see it here. Yeah, you can see it here. X goes from the negative side of the sphere to the positive side of the sphere. So our first set of limits is going to be our equation for the sphere. The only difference is now they're going to be solved for x, because that's going to be the variable we're integrating over first, which means these limits need to be x values. So the lower limit would be negative square root of 16 minus z squared minus y squared to positive 16 minus z squared minus y squared. And the reason I wanted to do this one first is I just wanted to show you kind of a parallel between the two. Notice x was the only one that had a negative and positive limit here, Well, X is the only one that has a negative and positive limit here. We didn't do the other two, but they're going to both start at 0 because X is the only one that had a piece of the curve over in its negatives on the negative side. So now that we've got that done, we can now draw what this looks like in the YZ plane, which is a quarter circle. And depending on which variable we want to do next, we could either say, okay, well, that's going to be what Z equals square root of 16 minus Y squared, or Y equals square root of 16 minus Z squared. It's very symmetric. So to be honest, you can use either one next. You might use whatever the function is to decide the order after that, whatever is going to make this easier to integrate. But if we're not worried about it, or if we're doing it with technology, we can just do it arbitrarily. Let's do DZ next. 0 to square root of 16 minus Y squared. And then lastly, we can see that Z is going to go, remember that the radius is 4. Z is going to go from 0 up to 4. I'm sorry, I did Z already. Y is going to go from 0 out to 4. Guys, these will give you the exact same answer, okay? This is one where the order really doesn't matter at all. We might decide the order based off of what the function is. But if we're using technology, we might not care. We just want to put it together, whatever makes more sense for us. Questions about this one? Like I said, I've got a few we're going to go through. I really want you to feel comfortable with this part. Before you go try the homework or before you try any on your own. All right. Now, just like double integrals can be used to calculate area, triple integrals can be used to calculate volume if we set our function to 1. So what I'm going to do for the next couple is I'm just going to worry about finding the volume of a region. That way we're not worried about what the function is. But if we were integrating over a function, we could always just put the function in. Because again, the focus here is setting up the limits. If you can set up a triple integral, I'm confident that you guys will be able to solve it because we can always use technology, and you guys have done well with the double integrals. All right, so here's one. The volume of the region is bounded by Z equals X plus Y, Z equals 10, and the planes X equals 0 and Y equals 0. All right, so I have already put this one into Calc plot. So let's bring that over. I don't want you to lose the problem. This one is on the worksheet as well. The next 3 that we're going to do are all on the worksheet. So obviously you guys won't be doing those. But they're good problems because they're not super straightforward and they really help us understand what it means to find our limits. All right. So we've got a solid trapped between all these planes, right? So here would be the top of the solid, this triangle. We got this purple side kind of making the bottom. This pink side's making one side and this blue side's making another. All right. So that's our little triangular prism in there. So that's what we need to try and find. We can actually maybe cut this down a little. Let's see if that makes it look any nicer. That didn't help. Oh, because I did the wrong one. Sorry, I meant to do this. Not really. But hopefully you guys, so this is important. We need to see that solid. And so here's what we do. You look for a definite top and a definite bottom, or a definite left and a definite right. And this is one that can be done in multiple orders. I'm only going to do one order for today, just because of time's sake. But we could do from the pink out to the purple here first, or we could do the blue out to the purple first. But what I think is easiest what stands out to me when I see this curve is I see that the blue plane forms the bottom and the yellow plane forms the top. Now, I put these in so I know which equation goes with which, but if you're ever not sure, turn them off, turn them back on. So that's the plane z equals 10 right there. That's the plane z equals x plus y. So I'm seeing x plus y as the bottom and 10 as the top. All right. So let's go ahead and take a look at that first. So that means, I'm just doing an integral of 1. And these, let me move this. Where should I put this? Okay, right there. You can still kind of see the form, but I want you to see the equations too. This is already solved for z, and so is this. So this one you might have been able to do without having to look at the graph, just knowing that 10 is going to be above the graph x plus y. So it's going to go from x plus y up to 10, and z is going to go first. All right. Now, here's what's cool about that. It has just turned a 3D region into a 2D region. All right. What do I mean by that? Well, now we get to look at our curve in the XY plane. Now, I refer to it as a shadow region, and this is a perfect example of why I refer to it as a shadow region. This triangle here is going to be the region we need to look at. But notice that triangle doesn't actually land in the XY plane. It's shadow. If there was a light straight above this curve, it would make a shadow that would show that line right there. So that's important because, again, that is the region we want to look at. And one of the things you can do with the plotter that can help is if you go to view settings, we can view above, in this case, the XY plane. Whoa, it zoomed us in way too much. That didn't come out quite as nice as I was hoping, but that's because the yellow is so defined. But look at what we have here. Here's our region. I know it's not really clear. What you can do if you're having a hard time seeing your region is you can always change the transparency on some of these. So you can start to see your other curves, and sometimes getting rid of the, I don't like that. Getting rid of the edges can be a little helpful too, right? So there was that plane x plus y. We know that this is, whoops, geez, sorry about that. Accidentally dragged it. Let me do that again. So we know that this is one of our boundaries. We know that this is one of our boundaries because this is y equals 0. This is x equals 0. This line is our other boundary. So let's draw that because that's what we need next. So we're now in the XY plane. And here is our region of integration now. All right. It's this triangle, and we need a formula for this triangle. Well, basically, we need a y-intercept. Well, let's think about the equation for this line. So I'm going to go back to the 3D, and let's make that a little bit less transparent because I want you to see something. Look at what's happening there. The plane x plus y is intersecting the plane z equals 10. That means this line of intersection is the intersection of z equals x plus y and z equals 10. To intersect those, we just set them equal to each other. And that is the equation of this line. All right, nothing fancy there. All I did was say, oh, okay, I need the intersection of this plane and this plane. So they're both equal to z. I'm going to set them equal to each other. As we know from double integrals, this region can actually be done in either order. It's up to us. Let's go ahead and just do dy dz. Not dy dx. Excuse me. Now, we need to think about, where this hits. Well, when X is 0, Y is 10. When Y is 0, X is 10. So let's say, so we're doing Y next. We can see that Y goes from 0 up to our curve, which solved for Y is 10 minus X. So 0 to 10 minus X. And then our last set of limits, X goes from 0 to 10. And that will calculate the volume of that solid that we saw. And if you ever need to get back into your regular 3D setting, same place under view settings, reset 3D view. There was our original view. All right. So that'll calculate the volume of that solid. Again, there's multiple ways to set this up. The problem is if I keep doing multiple ways for every example, we'll never get through them. And I'd rather show you more examples than more ways to do one example. Any questions about this one? How are you guys doing so far? Are you able to, I'm not actually looking for you to be able to just step in and do this yourself right now. You're still learning it, but are you able to follow where I'm getting these from, so that if you need to, you can go back and look at the video of class later. Make sure, double checking that I'm recording it because this is a good one. If you went back to this video, you can follow the way that I was able to set this up. So, just give me a yes in chat or a thumbs up. Okay. So I got a question. Why is 10 on top and X plus Y on bottom? If we look at our region here, I know there's a lot going on in it, but our region is this upside down triangular one. The reason X plus Y is on bottom and 10 is on top is because X plus Y is actually, for our region, is actually below 10, right? This is the X plus Y, this triangular shape here. That's the piece that comes through. It forms the bottom of our 3D region. So that's why it's the lower limit. This yellow plane is Z equals 10, and we can see it forms the top. So that's why X plus Y goes on bottom, 10 goes on top. And we'll see, there'll be other ones where it's actually a downward slanted plane and the bottom might be 0, or actually we're going to have one where it's like that. So we'll get to that. But guys, yeah, ask questions on this because I think this is one of the harder things to get the hang of in this entire class, only because of the 3D regions. 3D regions are hard for us to picture in our head. They're next to impossible for us to draw. So that's why we're spending a lot of time just going through the 3D regions. All right, then let's go on to the next one. Okay, yeah, we're gonna do a couple more. We're gonna do 2 more examples. Again, there's too much for us to go through all of them, but I want you to see just some different things going on. All right, so here's our next example. So this was an example. All right, so find the volume of the pyramid with a base in the plane Z equals -6 and sides formed by 3 planes, Y equals 0, Y minus X equals 4, and 2X plus Y plus Z equals 4. So there is a lot going on in this one, right? We got 2 equations, 2 implicit equations. So let's take a look. All right, so here is our 3D region. And again, let me show you how you can match up which plane goes with which equation. All right, so 2x plus y plus z equals 4. That's that turquoise looking one. And guys, you can, under settings, that's where you can change the colors depending on how you want it to look, whatever, if you want it to be a different color, if there's an easier color for you to look at, or if the colors aren't different enough, feel free to change them. All right. but this turquoise plane is 2x plus y plus z equals 4. All right. We also have the plane y minus x equals 4. Let's match that up with a color. That's this light green one. All right, it's cutting through here. That makes sense because there's no z in it. That's why it's got no angle in the z direction. So that's this plane. We have a plane at y equals 0. That should be our purple plane. It goes right down the y-axis. So that's that guy. And then finally, we got our plane z equals minus 6, which is this yellow guy on bottom. All right. Now, if we see what's happening here, I don't know why the plane y equals 0 isn't going up a little higher. Oh, that's probably why. Maybe. No. Why didn't it go up a little higher? Oh, maybe let's try it. Nope, that didn't help. That plane, remember, a plane extends in all directions. So this is gonna keep going up because that's gonna be what forms the top of our pyramid here. Anyways, I'm not too worried about that because I think you guys can see, like, if this purple plane keeps going up, you see where we're getting the tip of our pyramid or our rectangle, our triangular prism. So let's kind of flip this thing around. All right, so it's bound by these two, the light green and the purple plane and the yellow plane. We can flip it all around and we can see that that is a solid that is in there. All right, that solid that is right behind that green guy. So let's go back to standard before we go crazy. So this is going to be one where I think we are going to want a specific order of integration because doing the z first is going to make this a lot easier. Now, here is why. We can see that this yellow plane forms the bottom of our triangular prism and that this green turquoise plane, this greenish turquoise plane forms the top. So that already gives me my upper and lower limits on z. So z is going to go from -6 to this plane. It's just that this plane has to be solved for z. All right, so let's move our thing out of the way here. Hopefully you guys can still see at least some of it. And let's start to write up our integral. So we're trying to calculate the volume. It's going to be a triple integral. I'm going to start with the inside. Our integrand is 1 because we're just doing volume. And I think z is perfectly set up to do first on this one because we got a very clear bottom and top, and it's going to make everything else easier. Z is going to go from -6 to, again, this plane, but it has to be solved for z. So 4 minus 2x minus y. All right, that is our first set of limits. If you can get the first set, I think you're in good shape because, again, it now goes to a two-dimensional problem or a double integral. And we need that shadow region. Well, there's that shadow region right there. It's this triangle that's formed in the plane z equals -6. I know that plane was yellow on the top. It's purple when we turn it over. That is our region of integration right here. We have the y-axis here. We have the x-axis here. Let's draw what we have going on. So the reason I decided to start with z is I have a clear top and bottom. So first off, you guys have to see the region. If you're not seeing what I'm trying to integrate over, let me know. Because if you don't see this 3D region, then it's not, the limits won't make sense. But I see a pyramid right here. It's got, that's a side of the pyramid, right? Here's the bottom of the pyramid. Here's another side of the pyramid. And then finally, here's that last side of the pyramid. All right. So first off, we have to identify what it is we're trying to integrate over. So hopefully you're seeing that 3D region. Now, the reason I went with Z first, again, I very clearly see the bottom of Z equals -6. It is this yellow plane. That is what bound the bottom, and it's a nice constant. I also see that the top of my region is this slanted plane. It's the only plane that's slanted. So that is a very good top. And so, like I said, I'm able to identify the clear top and bottom to the region because of what I'm seeing here. And if I can do that, then that's what I'm going to start with. So we go from Z equals -6, which is the yellow plane, to Z equals 4 minus 2x minus y, which is this turquoise plane. Now, the next thing becomes making this a problem in the XY plane. Okay, now we got to be a little careful how we set this up. Notice this is the positive x-axis. This is the positive y-axis. So we need to take a look at what this looks like, and then I'll show you how we come up with the equations, but let's get a rough sketch. We can see it has a nice boundary here of y equals 0, and we've got an intersection point over here on the positive side. So it's doing something like this. Okay. Is that a perfect sketch? No, but we didn't need it to be. All we needed to do was get an idea, because we know how to integrate over a 2D region. So once we get the equations for these two lines, we'll be good to go. And then we'll talk about order. So let's talk about how we get the equations for these. And then we'll talk about the order of them. Right. And now, again, this is kind of a mirror image because this is the positive x-axis. The thing is, let's go ahead and look at the XY plane. I don't know. Yeah, unfortunately, because this guy is in the way, we don't quite see our region, but let's see if we make it a little more transparent if we can. It's not really showing up really well because we do have a line at y equals 0. Not really seeing the intersection of the other plane very well. Okay, actually, you can kind of see it, right? There's this line here. That's that line. Here's y equals x equals, is it x equals 0 or y equals 0? I got to remind myself. Here's y equals 0, so the x-axis. And then here's our other boundary, which is the turquoise plane, okay? Now let's talk about how we get those other equations. So we need to figure out what this looks like. And we know that this line is the plane y minus x equals 4. Excuse me. So, sorry, I got kind of thrown off here. All right, let me just reset that view. Okay. So I'm looking at this region right here. Again, this is the positive x. So right here, this line here is going to be where our main plane, our turquoise plane that I made a little bit transparent, intersects the plane z equals -6. Well, remember, that's going to be z equals 4 minus 2x minus y. And we're looking at where it intersects z equals 6, excuse me, -6. So just like we did last time, we can set those equal to each other. And that will give us that line of intersection. So we get 4 minus 2x minus y equals -6. So let's see, what's going to be the easiest? what I'm going to do is I'm going to put it in an x plus y form because I want to talk about something. So I'm going to add the 6 over and then add the 2x and the y over. So this basically translates to 10 equals 2x plus y. Again, notice which equation that is. It is this shorter one right here that's on the positive x side going up. So this line here is 2x plus y equals 10. Okay. All right, so that's one. And then we need this line, which comes from our other plane right here. Now it is where it intersects the line z equals -6 also, but this plane didn't have a z in it. In fact, let's do this so you can see where I'm talking about. We're looking at this line right here now. Well, that is basically just this plane, which we go back to the original problem, is y minus x equals 4. So this guy is y minus x equals 4. So, guys, we are in good shape now because, again, now we're back to what we've been doing over the past week, which is a double integral. So let's see, we don't even really need the 3D plot anymore. I'll leave it up here. But this is our focus from here on out. We took care of the first layer of limits. We're going to focus on these. Now, let's talk about order. Now we want to integrate over this region here. I see a definite left and a definite right. But if I try and do top bottom left next, I will have to do 2 integrals because I'll have to split it up here at this intersection point because my top bottom is different here than it is over here. We don't want to split it into 2 integrals if we don't have to. So we're going to do left, right next, which means our next set of limits are going to be for x. Okay. And that's how we decide. So that means both these equations have to be solved for x. So solving this one for x, if I add the x over, subtract the 4, I get x equals y minus 4. Over here, subtract the y and divide by 2. That one becomes x equals 5 minus y over 2. All right. I'm not doing anything crazy, guys. I'm just solving each equation for x. Here's our left. There's our right. So those are our limits on x. So we're going to go from left, which is y minus 4, to right, which is 5 minus y over 2. Okay. We have one more set of limits to go. That was for x. Our last set of limits have to be y. We can already see the lower limit on y is 0. That means we need this point, the y value of this point, in order to finish off this problem. Well, that's not too bad because we have both equations already solved for x. So we're just going to set them equal to each other and solve for y. So y minus 4 equals 5 minus y over 2. All right. If you don't want to deal with fractions, just double everything. All right. So for those of you guys who don't like fractions, just make it 2y minus 8 equals 10 minus y. It won't change anything. So we add the y over, we get 3y. We add the 8, we get 18. And that leads us to y equals 6. And there is our final limit. That will give us the volume of this 3D region. Questions about this one? We're going to do one more, so don't worry. So, okay, so the question came up if it was x equals 0 instead of y. Yeah, so I don't want to just overgeneralize, only because if it were the plane x equals 0 instead of y equals 0, we'd have a different region. It'd be over here. And then we'd have to take a look at what it looks like in the XY plane. Let's see. Well, we'll take a quick look. There's another one I want to go through with you guys, but if we don't get time for groups today, that's okay. Like I said, I think this is worthwhile. All right, so let's just change this up. And so basically you're saying instead of y equals 0, let's close that out. We make it x equals 0. Let me okay, we might have to expand our graph a little too. We'll see what happens. All right, so we want to put in x equals 0. So you just go down to x equals, change that to 0. And it put in a plane there for us in this light blue. Now let's see, do we have a region of intersection? Yes, we do, right there. So, okay, so let's talk about this then. We can write this one up. This will be interesting. All right, let me bring this out a little just so you can see that a little bit better. We need to go a little further in the y. Let's go to 12. Okay, so we do have a region enclosed by these 4 planes. Are you guys seeing it right here? It's this little triangular region here. The triangle's laying on the y-axis. Oh, okay, I misunderstood the question. Triangle. Yes, if the triangle was the same shape but flipped but rotated about 90 degrees, we would have the same thing. Or sorry, not the same thing. Right, we'd want to switch the order. And again, guys, this goes. I can't stress this enough. I know a lot of times we want things to be easy, and so hey, if we do this, then it's always this. We're not always guaranteed that stuff. All right. And that's why I'm really stressing looking at the graph in 3D and then looking at the graph in 2D, because I want you to make your decisions based off of what you see, not some set of rules, because it's hard to develop a set of rules for these because the regions can just be really, really complex sometimes. And that's why I'm really focusing on how we take the graph and find our limits. But yes, if that same image had been along the y-axis, we would have done it the other way first. So you look for things like a definite top or bottom, definite left or right. You'll hear me use those phrases very often when we're doing this. Let's go ahead and do this one. This will be interesting. Okay, so we can kind of see this region here. Actually, we're kind of distracted by all of that. Do we want to get? We don't really need any of the negatives, it looks like. Let's zoom in a little. Let's bring these. Okay, I guess lost the negative, that's why. Zoomed in a little too much. Oh, because we were going down to -6, that's why. That was. All right. There is our region right there. It's tiny, but we do have a 3D region, encapsulated by these 3 curves. We don't need to go up so high in the Z either. There, now we're seeing it a little better. Okay, so there's our 3D region that is enclosed by all 4 planes. Now, our top and bottom are actually the same as they were before. So we're going to keep that the same. -6. Sorry, I forgot the equation. 4 minus 2x minus y. So we're doing dz because, again, that's still the easiest to do first. Now we need this triangular region. And probably, if you want to see it from the bottom, I'm going to need to go a little bit further. Let's go to a -7. There's our triangular region we're looking at now. Okay. Now let's see if we can figure out what this guy looks like. Notice that it lies in the positive y. So actually, Trey, I think this is going to be very similar to what you were just asking. Let's move this plane out of the way. So no, I don't want to move it completely. Let's increase the transparency. Here's our region. And if we were to draw this in an XY plane, in a standard XY plane, so X on the horizontal, Y on the vertical, we can kind of see what this is looking like. Because here it's actually, it's actually even above the x-axis. There's a piece here and a piece here. So it's doing something like this. So Trey, to your point, yes, we're going to want to do Y second in this one and then X. Now we need to figure out what those lines look like. Now this line here, that's actually the same line as it was before because it's where this big plane intersects the plane, z equals -6. So going back, if we look at what that line was, it was 10 equals 2x plus y. And on our drawing here, that's this one here, 10 equals 2x plus y. So we just need this curve, which is this guy right here, which again is just this pink plane. It's pink from this angle, which is just this guy right here. The y minus x equals 4. All right. Now we're doing y, so we're actually going to solve both of these for y. So our bottom is solving this for y. We get y equals x plus 4. And solving this one for y, we get y equals 10 minus 2x. So there's our left, or our bottom, excuse me, because we're doing in terms of y, x plus 4, up to 10 minus 2x. One thing I want to point out, guys, we're doing a different region because I changed that one plane. So these answers, like if we were to compute these, will not come out the same. Okay. Now we do need the intersection of these two. We need the x value. So we're going to set those two equal to each other. So 10 minus 2x equals x plus 4. So add the 2x over, we get 3x, subtract the 4, we get 6. And that's going to give us x equals 2. So it's going to go from 0 to 2 in the x direction. And that would give us the volume of that region. So kind of made a nice little change, and it did exactly what you were asking about, Trey, as far as the order of integration. Now, guys, we could have done x second on this one. But again, because the left and right is different here than it is up here, we would have had to split this thing at this where it switches, and this would have been 2 integrals. And that's fine. The inside limits would have been the same on those, but we would have to do 2 separate integrals for it. All right. A little bit of a tangent there, but I think it's worth going through. The more you see of these, the easier they get. All right, questions about this one? Let's do one more. This is a cool one. All right, we're going to calculate the volume of this region. And I like this one, again, because very specific things going on that I want you guys to see. All right, let's bring this plot over. Had all of these set too big. All right, so there's the equations. This is the cylinder that you see there. The vertical plane y equals 3 is this guy here. The plane with a positive slope is this one. The plane with a negative slope is this one. And here's the region is this inside the cylinder. All right. Is everybody seeing the region okay? It's this triangular region that's inside the cylinder. It's being cut by these three planes. And so here's the point I want you to start to get to. Look at this. If I look at it almost directly from the side, you see how I see a bottom and a top to the region? Now I know it's kind of hard to see this plane when I turn it to the side, but remember that there. Oh, there's a good view. You see how I see a definite bottom and a definite top? That tells me I'm in good shape to do Z first with this is my lower limit and this is my upper limit. Sorry, I made everything too big. Where am I going to put this? What can we do? Let me do this. Sorry, the image is a little small, but at least now you can see everything. All right, so hopefully you're seeing this definite top and this definite bottom because that's huge. If I tried to do left, right, notice how the left and right is different here than it is up here, which already tells me if I did left, right, I'd have to split it into two separate integrals. Don't want to do that. So let's get the Z out of the way and get into 2D. That's kind of the way I think about triple integrals. The sooner I can find that first set of limits, the sooner I get back into 2D, which is something I can draw. Now, this again has a negative slope. So it's gone from the -3 minus 2y. They're already solved for Z up to the 3 plus y. And again, if you're not sure which plane is which, you know how to turn them on and off in the 3D plotter and check and make sure. All right, guys, that's huge because now we're back into 2D. So now I am going to bring this back up because I want you to see. Let's take a look at what it looks like in the XY plane. All right. Now, here's one intersection. Here's another intersection. And then here's the sides. And if you're not seeing it completely, just straighten it back out and you can kind of see what's going on. Oh yeah, here's what the part that we're looking for. So it's above this red plane, below this line, because that's the line of plane of y equals 3, and then inside these circles. Now, what's cool, what I like about this is now I'm going to take it over here and do my work. It's up to you if you want to draw the whole circle. You can. Oh my goodness, that is my circles. I feel like get worse and worse every day. Sorry, guys. We got a line going through here, and then we've got another line, which is the intersection of those two planes coming right here. Okay. We have to figure out where those are happening. Let me just want to clean this up just a little bit because it is important. That curved side is what's going to determine our order of integration. This picture is a little better. Notice if I try and do top bottom, well, the top bottom is different here than it is here and than it is here. So if I do top bottom, I'm looking at 3 integrals. Don't want to do that. But I've got a nice clean left and a nice clean right. Well, those came from this equation here. So I'm going to do X next. And remember, you know, like I said, you're going to get used to seeing this. The curve on this side is X equals negative square root of 16 minus Y squared. Yeah, Cooper.
When I look at that from the view of the XY plane,
yep,
I see a definite top and bottom, and I see 2 curved lefts and right. Can you show me what you mean by that? Because you were saying that if we did top and bottom, you see a top here, top here, top here, 3 integrals. I see just 2 definite lines.
Yes. If I were smart, I would have used this circle because it would have made life a lot easier.
Uh-huh.
Oh, I don't want to. How do I? I don't want a black circle. Well, that didn't help. All right, so actually I'm just going to use this because I don't know how to change that, but let's do this. I think this will help. Here's going to be a much cleaner drawing. All right, so that's that line there. And then we got this red line down here, right? Idiot. Sorry, guys. I want to keep that. There we go. All right. Well, I'm going to get this figured out. I want to do this in a way that makes sense to you guys. And then there's another line. Well, that didn't work. Okay. So a little bit prettier picture than my graph. Now, here's the concern, and this is where this thing gets really, really nasty, actually, even more so than what I was saying. Let me get a little bit different color. What are we using? There's blue. All right. Now, if I start to try and break this, so you're right, Cooper. There's a nice left and a nice right, which is why we're going to do that next. But let's just say we wanted to go top to bottom next.
No, so what I was saying was that I see a definite top to bottom. I see weird left and rights.
Okay.
Like I see it the other way from what you were saying we should do.
So so part of it, I think, is the way that I'm saying what I mean when I say a definite left and a right versus top and bottom. When I'm saying definite, I don't mean straight. I mean it's defined by a single function. So the left is defined by this curve here, and the right's defined by this curve here, right? Now, here's what happens if we try and do top bottom next. If I put in a vertical line like right here, well, the top is this piece of the curve, and the bottom is this piece of the curve. We'd have to do another one here, because now the bottom is this red curve and the bottom is this part of the circle. Then we'd have red to green in the middle, which would be great. But then as we get over here, the top is this part of the circle down to the red line. And then to the right of that intersection, we have a different curve defining the top and bottom now. So I was wrong when I said 3 integrals. We'd have to break this into 5 integrals, because the top and bottom are defined by different functions here than they are in here, than they are in here, than they are here, and then they are here. So when I'm saying definite, and I think that's, I probably wasn't clear enough with my wording. What I'm saying is defined by a single function. Did that help clear that up?
Yes. So if you wanted to find the top and bottom as a single function, well, you can't find them as there's 2 different functions, but you'd have to find where the circle intersects those points.
Yes.
And that'd be a pain in the ass.
Yeah. Right. Okay. Because now we're looking at 5 separate integrals.
All right. That makes sense.
I'm glad you asked that, though, because I mean, that's a good clarifying question of what I mean by definite. I see that the left and the right are defined by a single curve, which is why I'm attacking those next. Other questions at this point? I mean, this is why I specifically do this problem every time, because of this. I think it does a real good job of highlighting what I mean by a definite left and a definite right. And now you guys know what I mean, because now my wording is a little clearer. Okay, so the left is this negative square root of 16 minus y squared. The right is the positive of it. So we're doing 1. We already know we're doing dz. We're doing dx. So negative square root of 16 minus y squared to square root of 16 minus y squared. Now we are almost done. That's the nice part. We need our limits for y. And as we can see, y is straight lines on top and bottom. We just need what the values of those are. Now, the top one is actually pretty easy, because if we go back It's that one plane that is parallel to the z-axis. The only one of our equations that's parallel to the z-axis is this guy right here. So our upper limit, this upper limit here is the plane y equals 3. So we already know our upper limit. Our lower limit, there's a couple different ways you guys can approach this. Because if you're working with the graph, guys, you can turn up the transparency and you can pretty much tell where this intersects by looking at the scale on the y-axis. But let's talk about a more general way so that it'll always work. Well, what's creating that line? It's the intersection of these two slanted planes, right? Those two slanted planes came from these two equations. So what we're going to do is we're going to set those guys equal to each other and solve to get our last y value. So 3 plus y equals minus 3 minus 2y. So we end up with 3y equals negative 6, or y equals negative 2, which if we look at the graph again, makes sense, right? It's a little closer to the x-axis than this one was. So it makes sense that that y value be a little bit smaller in magnitude. And that will give us the volume of this region. All right, let's just reset that because otherwise it's just going to keep floating around like a space station. All right. So that will give us the volume of this encapsulated solid. Other questions about this one? Okay, then, guys, we're not going to have time to break into groups today, so I'm not even going to bother with that. I have one more thing I want to talk about, and then I'll mention a couple things, but one more thing I want to talk about with triple integrals. Just a couple notes, some rules of thumb that you can follow. Since triple integrals can calculate volume, they can also be used to calculate total mass of a solid, because mass is volume times density. So if we have a function that gives us, if the function in here gives us the density per unit volume, then what the triple integral gives us is the total mass. All right. So when we had the one before where we had a function, let's see, back here, if this was a density function, we'd be finding the total mass of that solid. So that's one of the things that we can do with triple integrals. Another thing I want to point out when setting up a triple integral, and you'll see it in the ones that we've done, the outside limits have to be constants, just like with a double integral. The middle integral can only involve one variable, and that variable must be the last one you're integrating with respect to. So these had y's in it. That's okay, because we're still going to integrate out the y. The inside limits can involve two variables. It didn't happen on this one, but it happened on this one, right? Two variables on the inside, that's okay, because we're still going to integrate with respect to y and x. This one had one variable, x, that's okay, because we're still going to integrate with respect to x. So these are things you can kind of use as checks when you're setting up these integrals to make sure that you're at least getting the right idea. One thing that I really, I've stressed it a little bit with the double integrals, but I really want to stress with the triple integrals. Guys, use technology to calculate the integral. Because I want you to make sure you have it set up right first. Yes, there might be a triple integral you got to calculate by hand on the final. It would not be a really, really, really difficult one. So I don't want you to worry about that. So you do need to know how to do a triple integral by hand, But when you guys go to the homework and you're doing multiple of these, I really do think the biggest part of the problem is setting it up and getting the limits correct. And just every once in a while, do one of them by hand to practice doing a triple integral by hand. All right. But I want you to focus on setting them up. So as you're going through the homework and the problems are like what we were just doing, hey, use a triple integral to find the volume of the region bound by these curves or these planes, or these surfaces, I should say, not curves, surfaces. Once you set it up, go ahead and calculate it with Symbolab or Wolfram Alpha. Check it in more to see if the answer is correct. Because my big concern is this can obviously be a really long section if you go through calculating it by hand every single time, and what it was something was set up wrong. I'd rather have you calculate one by hand that you know is set up correctly than trying one where you're working on the limits also, okay? Because I just don't want you to get really frustrated on this homework and have it take an exorbitant amount of time. Again, for the final, I'm not going to, some of those regions we just looked at with the plot, I would not give you those regions on an in-class proctored exam. So when I say by hand, I mean, actually doing the integration by hand. So I would go ahead and do this problem by hand as opposed to putting it into Symbolab or Wolfram Alpha. I highly encourage you guys to use the 3D plotter to set up your region. We have access to it. Now, obviously for the final, you won't have the 3D plotter, but I wouldn't give you regions like the ones we just looked at on the proctored exam. This would be more like what I would give you on the take-home problems. On the proctored exam, I'd give you something you're very familiar with, like a half a sphere or a quarter sphere, because I don't want you spending a lot of time on one triple integral problem on the final, on the proctored final. That's what the take-home problems are for. Okay, so don't freak out and think you're going to be doing one like this on the proctored exam. This is more like a take-home problem. This is more like what you would see on a proctored exam, a surface that you're very familiar with, like a sphere, so that you can get the equation right away and do it. I don't want you stuck on one single problem. Okay. So I do want to make that very clear, because I get that can be nerve-wracking the first time you see these. Okay. All right, guys. So that is what I wanted to go through for tonight. Like I said, you guys came up with great questions, and I think that was worth the time. So I don't mind that we didn't get into groups today. That's totally fine. You guys do have access to the worksheet and the solutions if you want to try some of the ones in the worksheet. By all means, there's some good ones in there. We did half the worksheet anyways. Like I said, the next take-home problem is available, or should be available tonight. So feel free to get in there and go download it and, get started on it. Maybe there's one or two you'll be able to do right now, and you can get those out of the way. They're not due until May 20th. You got plenty of time. But I just want you to make sure you're aware that the first take-home problems for Module 4 are going to be up there tonight, since we're basically a week behind where we would have been had we not had that extra week for spring break. All right, guys, we do have some time left. What kind of questions do you have? And guys, if you don't have questions, we can absolutely end early tonight. We almost always go over. So, if you don't have questions right now, that's fine. Remember, I know I don't see you again until Tuesday, but you have access to online tutoring, both through SCC and BrainFuse. We have the forum for you guys to post problems. You can email me questions. Yeah, guys, triple integrals are a lot. They are. It's why I wanted to spend an entire class on this. Let it sink in, guys. I'm going to be posting this. I'll be posting this video after class. So you'll have access to this video. You can always go back and look at the video lessons. Just if you ever need to go back in, just use late passes. And don't forget, when you guys are doing the homework, you are going to have videos to help you through the homework. So don't feel like, that you're getting thrown out to the wolves here. You're still going to have a lot of support going through this. What I would say, this is a homework. Definitely start early, especially if this seemed like a lot, so that you have time to get help when you need it. All right. So make sure you get started on this one early and work, get help as needed. But yeah, guys, take a little bit of time to take this in.
I think I've actually got a question. Might be kind of a dumb one, but I still kind of have a question.
Let's hear it.
So when you're looking at the graph plotter, when you have the graphs up.
Let's bring one. Sure.
Yeah.
Here, like this one?
Yeah, like this one's actually a little bit more self-explanatory, but maybe one of the other ones.
Okay. This one.
Yeah, okay. So when you're looking at a graph like this, what are you looking for to say, like, oh, this angle's like 3 plus y, z equals 3 plus y, or this angle's this, or okay. What are you like?
Let's go back to the
look for. Yeah.
Okay, so here was the problem statement on this one, right?
Right.
Now here's the thing. All of these planes were made by these equations.
Right.
So these equations are going to be involved in our bounds. So I'm not, we don't have to do a ton of calculating. So what I look at, so first I look at the region, identify, what's enclosed, which is, right, this triangular prism here, right?
Right.
And so then I look for, okay, I see a bottom and I see a top being made by this yellow plane. So then I need to think about, okay, which of these equations are making those? And one way of doing that is because I've already put them into the plotter. If you're not sure, remember, you can turn them on and off. Oh, okay. The purple one's made by z equals x plus y, and that's going to be my lower bound, and it's already solved for z. So I already know my lower bound, if I'm doing z first, is going to be x plus y. And then I got to identify this yellow plane. Well, that's going to be the plane z equals 10. So that's how I identify that my lower is z equals x plus y, and my upper is z equals 10.
Oh, okay.
So that takes care of the first limits, and that takes us out of a 3D problem, which I do think is helpful, because now we're looking at this triangle in the XY plane. And so now it's a matter of finding these three equations. Well, these are kind of easy for this particular one because one of them's x equals 0 and one of them's y equals 0. But this line is coming from the intersection of the purple and the yellow, which were the x plus y and the 10. So that tells me I have to set those two equal to each other to get the equation for that line.
Oh, okay. All right.
Did that help a little bit, Andre?
Yeah, it did. Okay. Yeah, because I'm like looking, I was like, man, I guess just needed a second look at it. That's all.
Oh yeah, take your time with it, guys. Like I said, this gets tricky, and it's because it's in 3D. That's really the only reason, because 3D is really hard for us to draw. We're very used to visualizing things in 2D, and that's why I said, get those first set of limits. If you see a definite top and a bottom, and if they're in terms of z already, that's great. If not, that's okay too. But get that first set of limits, because then the rest is a 2D problem. And that's a little bit easier because now we have something we can draw. We have something we're a little bit more comfortable with. So that's kind of what I want you to take from this. One of the things I want you to take from this is, yeah, it's really tricky at first because you're looking at a 3D image, but really all you got to do is get that definite top and bottom, which is this plane here on top, this on bottom, get those in there. And then the rest is a 2D problem. And once we have that graphed, we're back into what we were doing last week, which you guys were doing really well with. Other questions? Oh yeah, no problem, guys. Now we actually are at 6:30, so I know some of you guys have to get going. Other questions about anything we talked about today? And guys, don't forget, you can always email me questions, no problem. No problem, guys. I'll be putting this video up actually probably within the half hour. So anything you want to review,